Hey, what's up guys? So this is the continuation, the other part of 5.3. So in the first part we talked about exponential functions and their transformations, and this time we're talking about logarithmic functions and their transformations. So before we talk about the transformations, let's go over and make sure we understand what the behavior of the function of a logarithmic function looks like. So just to review, an exponential function, so y is equal to b to the x. Um, Now the exponentials are inverses of logarithms, and logarithms are inverses of exponentials. We covered that in the second lesson in 5.2. And so let's go ahead and find the inverse of this function, this exponential function, and see what we get. So to find the inverse, we switch the spots of x and y, and then we solve for y. Now, solving for y is kind of weird here, but I know that I can manipulate, or I can change exponential equations into logarithmic equations, into log form. So hopefully you guys still remember how to do that. So to do that, I have log, and b is always the base, so the log of my base is b. Okay. Now, Now, the argument, so the number that goes here we call the argument. The argument is the x, and what goes on the other side of the equal sign is always the exponent, because logarithms equal exponents. Logs equal the exponents. Okay, so I know that y goes over here. So if I were to rearrange this in an order that you guys are familiar with, let me put y on this side and do y is equal to log base b of x. You can see that we have the inverse of the exponential function, which is indeed a logarithm. So these are inverse functions. Okay. So let's go ahead and graph and compare the two. I'm going to graph the function y is equal to log of x, when this means that the base is 10. Now the inverse of this function would be y is equal to 10 to the x power. Okay? So let's go ahead and graph these. So 10 raised to the x power, if we graph that, that's an exponential function, and we talked about those last time. Now, hopefully you guys remember, but in chapter 4, when we learned about inverse functions, we briefly talked about their graphs and how they are mirrored across the line y is equal to x. So, let's say, for instance, that we have a graph here. Let's say we had the line y is equal to x. Okay, so this is y is equal to x. Let's say we had an exponential, so our current exponential looks like this. So if we mirror this function across the x-axis, we should get something that looks like that. So that is a mirrored reflection over the x-axis, or not x-axis, over the line y is equal to x. So let's see if that's something that we get. So log of x, keeping in mind that your calculator automatically puts in the common logarithm when you use the log button. So if I do graph, and there you go, you can see that it's a mirrored function over a line y is equal to x. So this is what we call here, this is your log of x function. And this right here is your exponential function, b to the x. And there you go. That is what that's the comparison between an exponential and a logarithmic function. So this right here is your log functions, and this is what we're transforming today. We're transforming these right here. Now let's also keep in mind one other thing. So I'm going to, I guess I can just make a copy of this. And I'm going to use this space on this other page. Okay. Now, remember that we could also have decay function. So that's when it looked like when it came from this side, went up like that. So if we mirrored that over the x-axis, what would that look like? Or sorry, over the line y is equal to x. So again, we would get this if we had a base. So this is b to the x if b was less than 1 but greater than 0. Okay, so it's kind of hard to see what that might look like. But if we mirrored that over the x-axis, just keep in mind that it would look different, not like the one over here, and we will actually cover a specific example of that in just a second. So we'll see what that looks like. Now, onto the transformations. The transformations apply the same way as any other function, right? It's a matter of what is inside, what do we classify as inside? So what is inside? This is important because this tells us what's a horizontal change. This could be horizontal translation, a reflection over the y-axis, or a horizontal stretch or shrink, because whatever happens inside is one of these three transformations, versus what is outside. This is vertical transformation, which means we'll have a vertical translation, a reflection over the x-axis, or a vertical stretch or shrink. Okay, now in other functions such as the parabola, inside counted as inside these parentheses. For absolute value functions, it was what was inside the absolute value lines. For radical functions, it was what was inside the radical. And then outside just meant what was outside of these lines, or parentheses, or radicals. And then, just as a quick reminder, exponentials, basically what was inside meant what was inside of your exponent. So what went inside the exponent versus what was outside, which occurred out here or multiplied out here. Okay, now for logarithms, it's basically what is inside here. This is called the argument. So log base b of x is equal to y. Now x is the spot of the argument. Call this the argument. Okay? So basically what's part of your argument is what counts as inside. So in these cases right here, the log of x minus 4, this is inside, so this is a horizontal movement to the right 4 units. Okay? Also, so this is, and then this is addition, so this is a translation. So translation. Okay, but then you could also have log of negative x, so being multiplied by negative is a reflection over y-axis. And then you could have we call it a times x, so it's being multiplied inside. This is a horizontal stretch or shrink, depending on the value of the, so if it's greater than 1, it's a shrink by a factor of its reciprocal. And then if it's less than 1, it's a stretch by a factor of its reciprocal. Okay, now just the reverse opposite pretty much of what's going on is on the outside. So if it's something like log of x plus 3, now if you don't see any parentheses, so like up here, here we have parentheses. If you don't see any parentheses, you're going to assume that this is outside and not part of the argument. So you're going to assume that it's a vertical shift up or down. So this is vertical translation. Alright, and then if you have negative log of x, because it's being multiplied on the outside by a negative number, this is a reflection over x. Okay, and then if it's multiplied by a number outside, so a times log of x, this is a vertical stretch or shrink. Now vertical, if it's greater than 1, it's a stretch. If it's less than 1, it's a shrink, which is the opposite of what the horizontal stretch and shrinks were. Okay, so hopefully that review was helpful. Now let's graph some examples here. So I have log of x is equal to g of f of x is equal to g of x. Okay. Now, for my purposes, I want to see, first of all, I want to describe the transformations. So if I describe the transformations, there should be 2, I believe. So hopefully you can maybe take a second, pause the video, and see if you can identify them yourself before I go ahead and spoil it and give it away. But I noticed that all the changes are happening inside of the argument. So that means they're horizontal changes. So I know that because it's being multiplied by a negative number, that's a reflection over the y-axis. And it's being multiplied by 1/2, and it's inside, so it's a horizontal, and that's a stretch by factor of 2, so a factor of its reciprocal. Horizontal stretches and shrinks are always stretch or shrink by a factor of the reciprocal. Okay, so those are the 2 transformations. So graphing this, I'm just going to draw my x and my y-axis this way. So first of all, let me go ahead and draw the original function, which is log of x, just to remind people what the log looks like. So it should look something like that. Now the transformations, if we follow the transformations, it's a reflection over the y, so it's going to go out that way, but it's also a horizontal stretch by a factor of 2. So that means I'm going to stretch this horizontally, so it should look something like this. But because I'm stretching it this way, it's actually going to come out a little bit more like that, because it's stretching horizontally. So here's my function, but it's going to come out more like that. So this one comes out a little bit more wide above, but this one kind of cuts in a little bit quicker. That's because it's a horizontal stretch by a factor of 2. Alright, so that's those are those functions. Now let's talk about these functions right here. So now I hinted at here, what would you do? So remember here that if the base was less than 1, you would have a exponential decay function, and if you reflected that across the x-axis or across the x-axis, what would it look like? So let's go ahead and see what that would look like here, because these functions have a base of 1/2, which means their inverse function, which is an exponential function, would be 1/2 raised to the x power. So again, this would be an exponential decay function. So let me go ahead and just graph this in a calculator first to see what it looks like. So if I pull this up in my calculator, so I'm going to graph this. So log of x. Now, this is something that we haven't gone over, but this is how you graph something, or this is how you put something into a calculator that doesn't have a common log base. And we'll actually talk about this next time. Okay, so there you go. There's your function right there. Let's compare that to just log of x. Okay, so that's a reflection. So I guess that's what it would look like, the inverse of it. So it's kind of like the opposite of a exponential. So exponentials, you have growth and you have decay. For logarithms that have a base greater than 1, it looks like that. If you have a base less than 1, it's going to look like this right here. So we should expect our function to look like this right here. Okay, so let's see if we can see what's going on here. So that's what that function looks like. So let's go ahead and actually graph that so that we know what we're trying to transform. So here's my y-axis, here's my x-axis. So I know that my function is going to start up here and go up like that. Okay, so let's list the transformations that are happening. So out here I'm multiplying by 2. Since I'm multiplying by 2, that is a vertical stretch by 2 because it's outside and I don't use so it's a vertical stretch or shrink, and vertical stretches or shrinks you don't do the factor of the reciprocal, just as the factor that it is. And then inside the parentheses I'm adding 4. So inside is a horizontal change, so this would be a horizontal translation left 4 units. Okay, so this function will go to the left 4 units. So this is like, I guess you could call the asymptote, right? The exponential function had the asymptote, so this is going to be moved over 4 units. So I should expect my function to not exceed to the left past this point. Okay, so there's where my new function is going to be g of x. So it's going to be moved to the left 4, but then it's also going to be a vertical stretch by 2. So that means we should expect it to kind of go down more. Instead of, it's going to come out more because of the vertical stretch. So I should expect it to come right here, but it's going to go out more like that. That's compared to this one, which kind of came like that. So the vertical stretch is going to pull it, so it's more vertical. Okay, and that should do it for those ones. Now let's go over here and talk about writing a transform exponential function. So let the graph g, so we're talking about exponential functions, not logarithmic functions. So let the graph g be a reflection in the x-axis followed by a translation 4 units right of the graph f of x is equal to 2x. So my suggestion here is to use the sheets that we have up here and up here when doing these type of problems. So for example, I'm going to list the transformations as the notation. So use the notation column first. Okay? I'm only going to be looking at the notation column. So let the graph of g be a reflection in the x-axis. So f of x, whenever it's a reflection in the x-axis, reflection in, the x-axis, that's going to be this, negative f of x. So write that down. So negative f of x. Okay? I'm going to apply this transformation first, and then I'll do the second one. But let's first write down what this is right here. Negative f of x, when applied to this function right here, means negative, and f of x is 2x. So 2 to the x, which is just negative 2 to the x power. Okay, so that's the first transformation. Okay, now let's go up here, and it says followed by a translation 4 units to the right. Okay, so that's a horizontal translation because it's to the right. So that's going to be like this. So x minus 4. So actually, it's going to be exactly like that. So if I put that in this notation, it should be x minus 4. So this is going to be, I'm going to list the next transformation, which is f of x minus 4. Now if I plug that into this function right here, remember that this is an input. X minus 4 is an input. So make sure to use your parentheses. We talked about this a lot in composition of functions. Imagine this like a composition of function. X minus 4 is like a function, right? So I do negative 2 being raised to the x minus 4. So I'm inputting this into the x location right there. Okay, now this right here is g of x. We applied all the transformations that it asked for. And that right there is g of x. Okay, let's give it another go with this one right here. And if you can, try it on your own first. So this one is a logarithmic function. So I'm still going to do the same thing. So let the graph of g be a translation 2 units up. So if I look at the notation table, 2 units up, that's referring to a vertical translation. So that's going to be f of x plus k, where k is 2. So k is 2. So f of x plus k, and k is 2. So let the graph of g be a translation 2 units up. Of this function right here. This is the function we're talking about. So if I do f of, whoops, I gotta make sure that I write it correctly. F of x plus 2, it's a vertical, so it's outside. So I'm doing that to this function right here. So f of x, so I'm going to write this as it is. This is saying f of x, and I know f of x is that right there. So log 1/3 of x, that's a f of x, right? And then plus 2, so then just plus 2. Okay, so if we want to write it without any parentheses, which we can, this is log base 1/3 of x plus 2. That's the first one, but then it says followed by a vertical stretch by a factor of 2. So let's look at what that notation looks like. A vertical stretch, so vertical stretch, a stretch by 2. So this is the notation. So a times f of x, and a is equal to 2. So 2 times f of x, which is equal to, so I am making f, so this is what I'm referring to my f of x. So I'm going to do 2 times by f of x, which is log 1/3 x plus 2. Remember that 2 is not part of the argument here. So knowing that, because it's addition here, it's split up, so I have to distribute this 2. So this is going to be equal to 2 log base 1/3 of x plus 4. And this is equal to g of x. Okay. Alright, so that should pretty much do it for us today. We will go over next time 5.4, but that does graphing transformations for us, and it completes this section.